Sorry, I'm late a little bit. So what are we going to do today is move on. We'll let those details of the Fibonacci heaps and binomial heaps for office hours, and we're going to move on to graphs. One thing I have to say about the heaps implementation that you have to do for the homework is there is a fancy way to do a set union, which we're going to talk about, just not in time for you to do that implementation. We're going to talk about, when we talk about next week, about the Kruskal algorithm. That's where you're going to need to say, if I get two sets, how do I join them or combine them? So you have to dig that up a little bit, I think, for a fancy implementation. Now, if you want to do more naive implementation of binomial heaps, you can probably use all kind of arrays, lists, trees, whatever. But in practice, you need this efficient union, disjoint set union. It used to be a chapter in the book. I don't think it's a chapter anymore, but it used to be one in the second edition. The union sets. How do you deal with sets? So this is something that a fancy heap will need to have. So what I want to do is to move into graphs. Let's say part A. Because we're going to talk about graphs essentially until the end of the term. This is our biggest topic for the second half of the term. So about 3 weeks or so will be all on graphs. Let me see here. We'll get to this in a second. I'm going to ask you that question if you want to think about it. When people naturally see a graph. So of course we're going to use graphs in computer science for many purposes, but are there any natural graphs? Since it just happen in nature that way. We'll get to that in a second. So G is a graph. It's usually something like this, where we use a set of words. Or nodes. And they give this E set of edges. This is typically a BU from one vertex to the other vertex. U, or sometimes we just put this aside. So a pair of vertices. It's an edge. Sometimes you can call it a connection between vertices. Here's an example. I have here 5 nodes. And I have the following edges between them. Example graph. How many people have seen graphs before? Everybody? This is a required prerequisite, right? So today I'm going to go lightning fast to a bunch of things that I'm assuming you've seen before and maybe you need a little recap. Next week I'm going to slow down in doing more interesting things. but today is going to be a marathon of all the things you're supposed to already know about graphs. So how do I represent this? I can build an adjacency matrix, which is, I have 5 nodes, right? So it's 1, 2, 3, 4, 5 times 1, 2, 3, 4, 5. And if I see edge 1, 2, what do? I go to 1, 2, and I say that's a 1. That 1 corresponds to, this here is who? Edge 1, 2. How about if I see 2, 1, that's also an edge. I'll go to 2 and 1 and say this is here edge 2, 1, right? How about the 5, 4? Or let's say 5, 2. 5, 2 would be 5, 2, right here, that's a 1. So this is edge 5, 2, and 2, 5, it's right here, that's a 1. So this is edge 2, 5. And everything that's not an edge, for example, what's not an edge? 5, 3, right? Or 3, 5, that's not an edge. So 3, 5, right here will be a 0. That is now edge 3, 5. Similarly, 5, 3 will be a 0. So in a DHC matrix, I have ones when I have edges, 0 when I don't have edges, right? And I can represent the same graph. Instead of doing this matrix, I can do it with adjacency lists. How would I do that? I write the node 1, say that's the node, and I build a list of all nodes connected to 1. So what is the first node? Say 2, right? So I'm representing a memory. I have put here 2, and this is a pointer to the next object, also connected to 1, which is 5. So this would be a 5, and this would be a null pointer because after 5 there's nothing in that list. How about if I write the 2? Who's connected to 2? 1. Who else? I have a long list here. So that's say 3. Next one is 4, and next one is 5, right? And then no. Let's do one more. If I want to write down, say 4, I get connected with 2. It doesn't have to be in a particular order. I can do the 5 first if I want to. And then the 2, and then the 3, and then no. So in this matrix representation, how much storage is here? How much space do I need to store this?
V squared. Sorry, V squared.
V squared. In here, how much storage do I need? So this is an abuse of notation. What we really mean by that is, of course, maybe V with bars, the size of V. Typically, the size of V is n. So when you see in a graph n, that means the number of nodes. How much storage is in here? How many blocks I have? How many of these blocks are here? 2e, right? You could say 2e because it changes twice, but that's the same as O of v, right? A constant doesn't change, the asymptotic. Is e the same as v squared? Not necessarily. So how big is e in general? Is at most v squared, right? Because that's all pairs, and at least
N minus 1. Mod V minus 1.
0. Graphs don't have to have edges. This is a valid graph. It has 3 connected parts, right? So I don't, this is a disconnected graph. And also the other thing that we didn't say here, this is an undirected. Very important concept. Undirected means what? Edges have no direction. That is what is undirected. Edge UV is the same as edge VU. So for undirected graphs, I think sometimes people call it symmetric, but that's not good. But maybe you heard sometimes symmetric. Symmetric technically means something else. So a very questionable name here. It's that the edge UV is the same as edge VU, and that implies in the adjacency matrix AUV is the same as AVU. Right. Means in this matrix, things whatever is an edge, it's got to be an edge the other way. Whatever's not an edge, this would be no edge the other way. If I want a directed graph, so here's a directed one. That is where edge UV is not the same as edge VU. I could have something like this, right? If I write the adjacency matrix here, 1, 2, 3, 4, 5, 6, versus 1, 2, 3, 4, 5, 6. What do I get? This is my adjacency matrix. There is a, from 1 there is an edge in 2 and 4. So from 1 I have a 2 and a 4. From 2 I've got an edge to 5. So from 2 I got an edge to 5 right here. From 3 I get an edge to where? 5 and 6. From 4 I get an edge to 2. From 5 I get an edge to 4. From 6 I get an edge to. That's the edge matrix of the graph. Everything that's not printed there is a 0. Right? If I want to build lists in here, say for 1, how my list going to look like? Same thing like before. I get a 4 and a pointer to 2, and a pointer to null. If I do this for say 3, I get a 5, pointer to 6. You have to know for a graph when it's directed and when it's undirected. This is very rarely left to, figure it out. Usually all problems will either say, or very explicitly or very strongly imply, it's a directed or undirected graph. When you choose a graph to model a problem, somebody's traveling through a bunch of cities, blah, 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 you should, from the very beginning, decide, is my graph directed or undirected? All right. So what's a path? That's the next coming up, right? Path. Sequence connected edges. So in this example here, I can say I have a path 1, 2. That's one edge, right? But it's nevertheless a path. I can have another path that says I start from 1, I go to 2, from 2 I go to 5, and from 5 I go to 4. That's a path. Right? 1, 2, 5, 4. I can have another path that says I go from 1, 2, 5, 4, and from 4 I go back to 2, which I've already been in. That's, in general sense, that's an acceptable path. Right? But more specifically for this thing, we're going to call something cycle. It's a path that ends where it starts. That would be, for my example, 2 goes to 5, goes to 4, back to 2. That's a cycle. And can I say, how about this cycle? 1 goes to 2, goes to 4. Sorry, 1 goes to 4, goes to 2. 1 goes to 4, goes to 2, goes back to 1. Is this a cycle? Why not? 2 to 1, this is not a valid edge. Directed edge. So this is incorrect as a path or as a cycle. So the general rule is if the graph is undirected, edges work, I'm saying work in a generic sense, both ways. I can go on any edge in whatever direction I want. If a graph is directed, edges work only in that direction. I'm not allowed in a directed graph to use this edge backwards. Now, in a directed graph, if I really want to have edges from 4 to 2 and 2 to 4, or I want to have, like I had here, from 2 to 1, how do I represent that? I need to have 2 edges. I may have another edge here. And if that's the case, then this edge is effectively undirected. I can use it this way, or I can use it that way. Good. Paths and cycles. Since we are here, let's define formally what a tree is. What is a tree? It's a graph DE, right? That must have a property that is connected. So first of all, what is connected for a graph? There is a path from any U to any V, any U node to every V node. So the sign of the path is some curly arrow like this. That's a path, and this is what? Edge. Right? So when you see this, that's an edge. That's a path. So when people put a straight arrow, that means an edge. When you put a curly arrow, that's a path. It involves, it's like an edge, it just goes through few nodes before it reaches there. Right? So connected means there is a path from everywhere to everywhere. Has to be connected. That's property number 1. Property number 2? No cycles. So for trees, you could still do directed or undirected, right? The thing is, in a tree, here's a tree, how it looks like. This is undirected. Right? Typically undirected. Let me put this word here, typically. So if nobody says anything about a tree, just say, okay, it's undirected, like this, right? I have no cycles here, and everything is connected. But on a tree, I have another property. I can choose a root. That's kind of a top node. Note in here that I can choose any node as a root. This choosing a root would imply a direction on edges. For example, suppose I pick this root right here. How are the edges directed now if I pick this root? Out, right? So this, everything goes outwards. If I want to put directions, doesn't mean I have directed edges anymore. Even if I pick a root, if I keep on directed edges, I can still go from here to here. Right? So I can have an implication of direction of edges if I wanted. Usually I can pick any node as a root, and sometimes what people do, they put that root at the top of the drawing, right? And then they draw the tree under it. Many trees are drawing with the root at the top. Okay? Which is kind of funny, it's the opposite of how actual trees grow, right? Trees have the roots on the bottom and they grow out, but for some reason we don't like to draw them that way, we like to draw them this way. Okay. So I'm not saying trees, once you pick a root, have to be directed. I'm saying if you pick a root, you can have a natural direction on the edges if you want to. So is it true that once I pick a root, say I don't have direction on the edges, every pass from U to V must pass through the root? Is that true? No. But what is true? If I pick two nodes in here, U to, say, to this V here, I say the path in a tree from U to V, so in a tree, the path from U to V is unique. Is that true?
Yes.
So any two nodes I pick, the path to go from there to there in a tree is unique. Assuming I use every edge once. So you could go here, then come back, then follow this. If you allow this edge back and forth twice, then the path is not unique. There is a path going straight, and there's a path that goes back and forth. So this is saying, assuming use every any edge once, so I can't go back and forth. All right, so that's a tree. Paths and cycles. Let me talk a little bit about this famous algorithm, BFS. Useful for quite a few things. BFS stands for So graphs, traversal algorithms can work for directed and undirected graphs, but keep in mind, if it's a directed graph, the only way I can use the edges is in the direction they are given. Right? So how about this graph? S, A, B, C, D, E, F, G, H, and I have the following edges. S goes to A, B, C has an edge this way, E goes to B, A goes to E, E goes to F, G, H, G goes to D, and the other way. H, I think I've got everything here, no? A goes F, this way. No, I think I got it. No, A goes to E. So here's an example graph. BFS starts in some node. Start node S. So I start writing S. Goes by waves. So S along the set S is wave 0. Next wave is what's immediately reachable from wave 0. Right? So the wave, what's reachable, so you can think about it like this is a wave 0, it only contains S. What's immediately reachable from S? A and B. So A and B, wave 1. Now what is reachable from wave 1 but not discovered or reached already? Right? I don't want to go back, this is all done. So what's discoverable from A and B now?
E and D.
E and D, how about C?
No.
No. So I get E and D, that is wave 2. And then, so this wave, it's a little funny. This is wave 1. This is wave 2. So now what's reachable from without C, right? So what's reachable from E and D? Okay. Is everybody reachable?
Yes.
So C, F, G, H. That is wave 3. So why is it that so every time I move to next wave, I'm not including, it's quite possible that, for example, from D, I can reach back to B, say. But I'm not including B again in my next wave. It's always what I can discover next, right? So a wave contains only new, or there's this terminology, newly discovered nodes. And BFS assigns a discovery time. So BFS, discovery, or wave. Older books call it wave, newer textbooks call it discovery time. Time for each node. So you might see the discovery time is D function. Discovery time of S is 0. Discovery time of A is 1, which is the same as discovery time of B. Discovery time of E is the same as discovery time of D, that is 2. And discovery time of C is the same as discovery time of F, discovery time of G, discovery time of H, which is 3. So in many traversals, you keep track of at what wave did I discover that thing. Right? I'm going fast because I'm assuming you've seen BFS already. Did you implement BFS? Okay, it's a good exercise. How do you implement BFS? So I'm not gonna do it here, but when you do implementation, what kind of data structure is very useful, very easy to use? Cube. Use a cube. That is first in, first out. Can you give me an example of problem that requires some sort of traversal and BFS is the natural good algorithm to use? A crawler, right? Because in a crawler I start with some seed pages, right, on the web, and I want to go crawl more pages, but I don't want to go too deep until I explore the frontier. You can call in the middle of BFS, sometimes the waves are called the frontier. I've got up to here, that's what I am. I want to explore the next wave before going too deep in either side. Right? What other problem I can solve with BFS? So crawler, I keep track of what pages I have. I go to the next pages. Right? The links will be the HTTP links in that case. What kind of other problem I would solve with BFS?
Sudoku?
Huh?
Sudoku?
Okay, I don't know. How do you solve that with BFS?
Or you try all the possibilities of all the cells and not necessarily.
So what kind of graph problem, right? This I'm asking, is BFS shortest path from a given vertex, right? If I want the shortest path from S to somewhere, BFS will give me that shortest path, right? Because what's going on, the theorem of BFS, it says, if some node is in wave 3, take this node, H, right, is in wave 3. What's the shortest path from S to H? How many edges? 3. Is that guaranteed? Can it be 2? Can it be 4? If the BFS starts from S and puts H in wave 3, the theorem says the shortest path measured by number of edges must be 3. It cannot be 2 or shorter. It cannot be 4 or longer. Right? So let's write down that BFS theorem. It starts in node S if wave of some node H or discovery, that's the same function, is some value K, that means the shortest path between S to H, right, must be exactly K edges. Why is not possible for this shortest path? We should go home and prove this theorem. Okay. Why is not possible for this to be less than K? So why is not possible to have a path from S to H that's less than 3 if BFS is 3? If there is a path with, say, 2 edges, the first node in that path would be in a wave 1, and the second node will be all the nodes like H, which are at length 2 from there, will be in wave 2. Why is not possible the path to be bigger than K? Because I've already got the path of K, right? What's the path? S goes to B to D to H, right? So this is a guarantee thing. In fact, to to see a little bit more of intuition about this problem, you can think that BFS creates the algorithm traversal tree. So if I start from S and I only go through the edges that BFS, the traversal tree consists on the same, it's the whole vertex set and only the advancing edges. What edges did I use to advance from S? I used to B, right, and to A. What other edges I used to advance to the next wave? So that was wave 1. How did I advance to wave 2 to E and D? I do B to D. And how did I get to E? Do I use, I can use either this edge or that edge to advance here. Do I put both of them in my BFS? 3 or just one? Which one do I put? The one that actually the algorithm used to discover E. So that depends on how you implement it, right? Because you have a queue implementation and whatever edge tells you, okay, there's this node E in wave 2, maybe starting from A, then we put that one. If it starts from B, maybe it's from B. And then how did I get to F? From E, right? How did I get to G? Maybe from D. How did I get to H? And how did I get to C? So BFS creates a tree by just selecting the advancing edges. This is a very important output of BFS, something that I think some of you did not see. Everybody heard of BFS. I think most of you could easily implement BFS with a queue, but be aware that you should output in your BFS implementation the discovery time, the wave time. But that's not enough. You also need to keep track of the advancing edges of BFS. So that at the end of BFS, I don't only have the waves, I have what was reached from what. So I can use this advancing BFS tree for some problem. Right? So this is traversal tree, or sometimes it's called the BFS tree, or the BFS advanced tree. All these names mean the same. It's the output of BFS. What edges have been actually used? Okay, that's BFS. Nice and easy. How about the other one? What's the other one? DAGs. Right here. DFS stands for depth first search. Okay? Well, let's see. Here I have a bunch of nodes. I'm going to call them, I can use any notation for these nodes. Direct the graph, right? Okay, so I have this graph. Now in here, I have discovery time and I have finish time. suppose I start in A. So discovery time for A, which is the first node, is going to be 0 or 1 if you want to count from 1. This is a conceptual thing. If you want to implement it from 0, that's fine. So how does this look? I start in A and I say discovery. I keep track of 2 times in here. Not like in BFS, the wave or the discovery. I also keep track when I'm done with that thing. The notion of depth stands for what? Prioritize going deep as opposed to broad, right? So if I have an option, I explore a node and I could go to the brothers, same parent, different nodes, or I can go down deep from that node as a parent. I prefer the depth as opposed to BFS, what I prefer breadth, right? Okay. I'm sure you've seen DFS before. It's even like high school now, they do DFS. So if I start from A, where can I move next? Say. Let's assume my nodes have discovery time 1 here. Let's put 1 to not get confused with the nodes. Say I move to D, so I go D next, right? That means I'm using this edge, right? I'm gonna make these edges bigger because those are like in BFS, the advanced edges. Edges that allow me to discover new nodes, right? So now if I move here, D is gonna be discovered at time 2, right? So I'm gonna put here time 1, discovery time 2, discovery time. Now I'm in D, say I wanna discover E, right? So I'm gonna use this edge here. So E is gonna be discovered at time 3. And then from E, what can I do? I see this edge, right? Is this edge good for me? No, it doesn't take me to some other new node. Now, to do this properly, we would like to have a state of those nodes. So that state we're gonna call it coloring. So we're gonna add a color here. Color or state. Every time I discover a node, I make it some color, right? So I'm gonna say gray. That's a typical language from the book. That's why I use those colors. But if you don't like gray, you can color it pink. Okay? It's fine. It's a color that indicates what? So gray stands for what? So initially everything is white, means not discovered. Gray means discovered, but not done yet. Meaning I'm still exploring from this node. And black means done. Done means discovered and I explored everything from it, right? So finish exploring. From it. So initially, everything is white initially, right? So I start with init, all white. All nodes are white. So I see A, I make A gray. Now I go to D, and now I make D gray, right? And then I go to E, and I make E gray, right? And then I notice this edge, but this is now what colors? E is gray. A is gray. It means that's not a good tree edge. It's not an edge to create an advance. So I don't use that edge, right? So I'm going to skip it. Can I go anywhere from E? So what do I do? Right. So E at the next step is finishing time of E is 4. and I make E black. I'm done with E. I'm done with D. I come back to where I was, D. Can I go anywhere from D? Yes. Where? So this is A going to D. This is D going to E. This is E done. Then I go back to D, right? And I move now to F. Discovery time of F is 5. So I color F. This is A gray, D gray, E black, F gray. I just discovered F, right? Then I note that there's no other edge from F, so I'm done with F. So this finishing time of F is 6 and F is. Now I'm done with F. So this is black now, right? I can call them, I can put a big cross over them. It's done. This one is done? Done. But this is still in play, right? After done with F, I come back to D, right? That's where I came from. D was gray, so now what happens to D? So how do I do that? I say done, D, discovery, the finishing time is 7, and I color D. Okay? So I'm done with D, which means I go back to A. I notice this edge. Did I look at this edge before?
Yes.
No. Is it a good edge? What kind of edge is this? This is now gray to black. As opposed to, remember when I was looking at this edge, what edge was this? This was gray to gray. Now, of course, the big edges, these ones that I'm coloring big, those are always what kind of edges? The advancing edges are what? Gray to white. These are the most important three DFS, three edges. Like in BFS, is the edges that allow me to discover new nodes. That's why I make them big. But there's other edges, either gray to gray or gray to black, right? That I'm not using to discover new nodes. It's important to keep track of what kind of edges those were, because later on when I need to deal with the structure of the graph, of course I need the three edges to do the traversal, but I may need some analysis based on these other edges. So I would like to keep track of those, and I bet you happened to keep track of those when you did DFS last time. Did you? Did you output that this edge is gray to black when you wrote DFS the first time? No, so that's necessary, okay? To keep track of the discovery finishing times and what edges I've seen in my traversal. Okay, let's keep going. I'm done with D, I go back to A. What else can I do interesting here? B. That is a 3-edge, right, or advanced edge. So how do I do that? I go from A to B. That means the discovery time B. So B is discovery time 8, and I color B gray, right? I'm in B now. I notice this edge. What kind of edge is this? B to F. This is gray to black. How about this edge? That's the kind that I want to use, right? If I see a gray to white, that is a good one. So I go from B to G, and I say G discovery time is 9, and I make G gray. Now I notice this edge. Is that interesting? No, it's a gray to black edge, right? Can I go anywhere else from G? No. So G is done, right? So how do I do that? I say G done here. I mark the discovery time of G being. So G is finished at time 10, and G now gets black color. So I'm back to B now, right? Because that's what I came from. B is, how about this edge? No what? I will not even consider this edge because the way I'm considering edges from B, I'll go by the adjacency list. So I'll only look at edges that start in B. So I will not even consider this edge. I don't need to classify this edge now because I'm not going to see it. In B, I'm only looking at the edges that start from B. That is this one and this one, right? So I'm in B now. B done. So what's going on in B? This finishing time is 11, right? And B black. So I'm done. And now I go back to A. A is done. So this ending time of A is 12. A is black. This doesn't traverse my whole graph because starting in A, what's going on with C and H? C and H are unreachable. From A. So the reason I didn't get to this node C and H is because, how do I say that more formally? There is no path from A to C or from H to H. Those paths don't exist. That's why I didn't reach them. If there would be a path, would it be guaranteed that DFS will find it? Are you sure? If there is a path, can I say guarantee DFS will find that path? Yes. So because I'm blocked, I'm done. I blocked A. The moment I block the original node means I'm done. And I didn't reach all the nodes means those nodes are not reachable from A. Okay? So to continue, I start a new DFS. So that's the second run. DFS stay from C. I start from here. So then I'll have C. I continue my table here. Start in C. So this is start. Start in C. Discovery is time. Is the next time, 13. And I make C gray. Then I do what? I go from C to H. I make discovery of H time 14, right? And I make H gray. Then what? H is done, right? Because there's this only, what kind of H is now here? Gray to black. So H done. So the finishing time of H is 15 maybe. H is black. And then I go back to C, it's done. That thing is 16 times 16, and now C is black. So remember, I want to keep track of discovery times and finish times for every node. That depends on where I start, right? I mean, if I didn't start in A, suppose I start in, say, F, I will have a different discovery times and finish times. DFS definitely depends on where you start. I could have started in C, and then C and H would be first. And from C, can I reach everybody?
Yes.
Right? So the reason I had two DFS runs is because the first one didn't reach everything. But that's not necessarily true everywhere you start. If you start in C, you could reach everything. So it has to do with where do I start the first run. In most graphs, you have to start at random because you don't know where to start unless the start point is given to you, right? You start somewhere and you may be unlucky because there was a better starting point perhaps. Okay? Let's make these edges. Which edge I use here as a tree edge? This edge, right? So these big edges are the advancement edges. This is a very important concept, so we're going to want to write this down like we did for DFS. From A, what were the three edges? We went to B, we went to D, right? And this is the DFS 3 edges, or advancement edges. From D we went to E, from D we went to F, so that's B. From B we went to G, and what else? From C we went to. So now this is not one tree, right? It's a 2 trees. Why there are 2 trees? Because I had to run DFS twice. Every DFS run is going to produce a new tree, right? Every DFS run produces a tree. So we want the output of those traversal methods, not just the, I don't know, wave number or the order of the node, something like this. That was before in college. Now we want exact discovery and finish times for every single node. And we want, at the minimum, those trees. In DFS, it turns out, we also want the edge classification for all edges. Not just these ones are the 3 edges. And how do we know the three edges again means what? Is from gray to black. Let's define a back edge. I think it's called back edge. It's here somewhere. Back edge. That's from gray to gray. Did I have a back edge in here somewhere? At E, right? When I was at E, again, the notion of back edge versus 3 edge depends on where do I run the DFS and exactly the choices I make, right? If I started in F and I go to E, and then from E I go to A, what kind of edge is this then? That's a discovery edge, that's a 3 edge. So the reason this is a gray to gray, a back edge, it's because my choice of DFS, and even then, it may have to do with in what order I process the edges, right? Being here, I could have chosen a different way to go maybe. What if I go, for example, B first, then F first, then A? I guess that's still gray to gray, right? If I started in A and I go B, F, E, and then gray to gray, right? But this depends on how I run my DFS. So this is going to be a back edge. And then I have 2 kinds of other edges that are from gray to black. But there are 2 situations there. Forward edge is when the gray one is discovered first. So it's a gray to black, but gray is discovered first. The other one, which is called cross edge, is still gray to black, but the black one is discovered first. So let's figure out how this happens. If I have gray to black in here, what kind of situations I have? When I explored this edge, I was in A, and this node was done. It's a gray to black. Which one of the nodes, gray or black, was first discovered? A. So what kind of edge was that?
Forward.
Forward edge. How about this edge here? When I looked at this edge, I was at time, after discovering C at time 13, I see this edge. What is the situation? C is gray, because I just work on it, and this was black, right? But which one was discovered first, C or G? So this is gray to black, but this is a cross edge, because the black node was already discovered when I got to C. How many people follow me here? So you can have easily exercises that ask you to classify the edges. That would be easy, or more complicated, where it doesn't tell you anything, has to do with some crazy problem, and the edge classification solves that problem. For example, how do I know I have a cycle in my graph? What edge tells me you have a cycle? Gray to gray tells you have a cycle. Right? So we can write that down. In a lot of problems, we need to find cycles, maybe. So graph G, find the cycle. How do you do it? You run DFS and look for back edge. Back means gray, gray. So can I say as a theorem, if you run DFS and you never find the back edge, there's no edge gray to gray, for your particular run. Remember, you can run DFS from node A, I run DFS from node F or G or B, and it's still a valid DFS, but it's going to give a different edge classification, because my DFS starting here will use this as a 3 edge, and then we'll use that as a 3 edge, who knows. Can I say as a theorem, if you run DFS correctly from any node, you may have to run it several times if you don't finish exploring in the first run, and you're not finding a back edge, there are no cycles.
No.
Theorem exercise. Maybe we put this in the final exam. If you run DFS from any node you choose to, and there are no back edges, that means no cycles. That's our candidate problem number 1 for the final exam. By then we'll collect a bunch. This is a mathematical theorem. Is that true? That if anybody runs DFS from whatever nodes they like, but they can't find a back edge, then it means that graph has no cycles. What did you guys think about that? Since I'm here, I would like to talk a little bit more about those graphs with no cycles. Graphs GDE, directed. So edge have directions here. No cycles. How are those called?
Tree.
No, because this does not imply a tree. For example, I could have something like this. This is a directed graph with no cycles, but is it a tree? No. What is it? How's it called? Directed acyclic graph. It's a name you should know. DAG. Many modeling problems in many situations rely on DAGs. Remember dynamic programming? Remember when we built that arrows between problems and subproblems? It's necessary to not have cycles in those arrows because problems depend on subproblem. If I would have a cycle, it means there is no way to solve the subproblems first, right? that arrows tells me which problems I need to solve before I solve these other problems. And the reason I could solve them in an order to solve all the problems from like beginning to end was what? There were no cycles. So I solved the ones early on. Like if these are my dynamic programming sub-problems, the way we put the arrows, this one will be solved first because it's a dependency graph. Solve this. If you have this, you can solve now those two because they depend on that one, and now you can solve that. When you install packages in Linux, you know, RPM Manager or Yum or how you call it, Homebrew or whatever, right? You install packages. Packages must form a dependency that is acyclic. Suppose I have a cycle. Your package depends on my package depends on his package, and your package depends on his package. What would be the problem? I can't install any package because it's going to require a package that's not installed, right? Every time I say, you install the package, and say, no, I can't do it because I need versions first. Try to sign mine, no, I can't do it because I need that one first, right? This dependency among packages have to be acyclic so you can install it. I mean, people have got around that. If there is such dependencies, they create a package that installs all three at once, maybe. But in general, we look for dependencies that are not cyclic. Dynamic programming is a great example of that. The dependency of sub-problems have to be acyclic, so I can have a starting point and finishing point, right? So there is a theorem here for those graphs. I mean, we're moving now at the same speed as I just did the whole thing. Typically, all this takes about a month to do in an undergraduate class, right? There's a theorem here. Maybe you've seen it, maybe not. That has to do with DAG sorting. It turns out that DAGs allow a sorting of all the nodes in a line, so on a line, such that all the edges are left to right. So that's a very nice property of these DAGs. There is a way to sort them. Put all the nodes on one line, such that all their edges go left to right. So this graph, how would you do it? You put this one to the left, this one to the right. These two nodes, whatever, in the middle. There is no arrow between them, so I can put them in any order. And then I draw the edges left to right. So how can you achieve such a sort? If you know the graph is DAG, so there are no cycles. How can you do it?
Yeah.
You run DFS, and then how do you arrange the nodes?
Finish that.
Right, so that's a good idea. If you run DFS and you know you have no cycles, by the way, that's also coming from DFS because I know I have no cycles since I've seen no back edge. Now I say, okay, I want to organize the nodes that way. What would I need for all the edges to go this way? It has to do those discovery and finish times, right? To sort by something related to discovery and finish times. So what's going on in here? A tree edge has what kind of property of discovery finish time between those two nodes? Discovery of gray is definitely before the discovery of black because it's advancing from here to here. But in here, gray to gray, which one was discovered first? The right one is discovered already. That's why it's a back edge, because it's a newly discovered node pointing back to an ancestor parent somewhere, right? So that will be a problem in my sorting, but the good thing is in a DAG, there is no back edge. So I don't have to worry about those edges. How about in here? This is discovered first, and this is discovered later. How about here?
The other way.
Black first and gray. So what about these edges? Right? If I sort everything by discovery time, So this edge I don't need to worry about because there are no back edges in my DAG, directed acyclic graph. This one has discovery. So the discovery of this guy is before this one. The finishing time is how? This finishes first, and then that one. In here, I don't have to worry about this edge. In here, this is first discovered, then this.
Which is fine.
But then, how about the finishing time?
Black,
Backwards.
97.
In black first, and then gray. And in here, this is discovered first,
And finish.
and this is discovered later. And who's finishing first?
Black.
Black must be finishing first. So there is another theorem here for DFS. DFS is a much more important procedure than BFS. Allows to solve more complex problems than BFS. BFS is useful, but it only does simple problems. So there's another theorem of DFS times. I can have case 1, some node is being, this is the time axis. Some node is being discovered, and then it's finished. So this is when I discover and I finish a node, U, and then I discover some other node, and then I finish that other node. I can have another case that's saying, no, I discover node U, then from U I discover node V, right? That's from U I get to here somehow, or maybe there's a path. I get to here. Then I have to finish V before I finish U. So if V has been discovered from U, I got to U, I discover U. Then I get to V, I discover V. I finish V, and then I get back to U, I finish U. And there is possibly another case that says you can discover U, discover V, finish U, and finish V. That's not possible. So it's got to be one of the two cases. Either you start a node and you finish it before discover some other node, or if you don't finish U before you discover V, you first have to finish V before you finish U. It's like parentheses. You have to close the last one open first. Okay? So we have another exercise here. This is too easy to do it in the final. How would you sort those things based on DFS? You have a DAG, you run DFS, you notice that you didn't see any back edge, therefore no cycles. Your job is to put those nodes on the line so that all the edges, which might be 3 edges, forward edge, and cross edges, they all flow left to right. How do we do that? Keep in mind that theorem right there. Okay. For the last thing I want to do now, I'm going to connect my projector in a second, but I want to tell you guys two problems that are very, very famous. They're not necessarily, I mean, they're computer science, but it's something that's useful to know. More mathematics than computer science. There's two notions that you should know about graphs, and something that mathematicians have worked on for a long, long time. In fact, 3 notions. Let me erase this here. The first notion is the notion of Eulerian path. I don't know what I have that drawn here somewhere. Okay. So Eulerian path. All edges used exactly once. If I want to say cycle instead of path, I have the same property, all edges used exactly once, and because a cycle, I need an additional property, which is I end where I start. So here's an example. 1, 2, 3, 4, 5, 6. I have these edges. This is I think, undirected. One, I got this. 2 goes to 3, 5, and 4. 4 goes to this. 5 goes to 3, and 6. Can you find a cycle or a path in here that uses every edge exactly once? Remember the property of the path, you have to connect. Once you get to Boston, you have to go from Boston. You can't jump around. So is there a way in here to say, okay, we can go? In the interest of time, I'll show you how to do this. I start in 3, for example, and I go from 3 to 5. So 3 to 5. From 5, I go to 1, I think. From 1, I go to 2. From 2, I go to 4. From 4, I go to 6. I'm not sure this is going to work, but let's see. From 6, I go to 3, right? Okay. From 3, I go to 1. 3, 1. From 1, I go to
4 to 5.
5 to
2.
and from 2, so I'm done, right? I use all the edges once. So this is another midterm problem, the theorem here that you guys can take home and prove. There is an Eulerian path if and only if all the degrees of any vertex, it's even. What's degree, by the way? We forgot to say that. Degree of a vertex is number of edges incident in V. So the theorem says if every single node, is that true in here? Every single node has even degree? 4, 4, 4, 4, 2. If every single node has an even degree, there is a way to go across every edge exactly once and end up where you start. This is not that hard. It's something that we need to prove, maybe by induction, for example. And there is another notion that's important for complexity theory later on, that's much more difficult, that says you need to traverse every vertex once, not every edge. That's called the Hamiltonian path or cycle. Contains each vertex once. This is a problem. Hamiltonian paths in general are very complicated problems. Eulerian paths are not. So that being said, let me show you something on a projector. That's the last piece that you are supposed to know. We have the right jack here. If not. So a lot of this stuff is what you've seen. I said earlier, natural graphs. Those appear very naturally thousands of years ago. Things that have to do with navigation and roads and trade, a lot of trade. Both the physical trade, how do I move the goods, but the money trade, how the money change hands, it's also a graph. A lot of those problems have been recognized in graph by the Egyptians 5,000 years ago. Okay? They're not new things. But there is all kinds of theories that are very modern. So most of the stuff we know about graphs, mathematics now, a lot of discrete graphs, but also a lot of game theories which relies on graphs. It's developed in the last 100 years or so. So this is what I've showed you already on the board. And this is some examples of a path and some example of a cycle. And this is BFS, animated, wave 1, 2, 3, 4. Let's do it again. Wave 0, wave 1, wave 2, 3. Right. This is a pseudocode for BFS. Easy to see how to do it if you use a cube to keep the current frontier. That's how crawling works. They keep the current frontier and say, pick something from my frontier, explore from there, not in depth, but just get the next thing, and that's my next current frontier. The cube gets updated. What are the nodes just explored from where I want to explore next? Depth first search. This is the DFS runs. This wrapper only calls the runs. The actual DFS procedure happens here. And if it's not done, if it doesn't traverse the whole graph, then I have to do another DFS visit or run. So how does this work? What's the core in here? For every edge, this is saying for every B adjacent to you, that's essentially exploring all the edges from you. I'm in node U, and I'm saying what are the nodes reachable from you, which is saying what are the edges UV from this node U. So then, how do I advance? How do I know that's a good edge to go? This gotta be colored gray because I'm in U. How do I know it's an advanced edge? If V is white, then that's an advanced edge. Right? This animation of this, what you've seen on the board, with discovering finishing times. Right? 2 runs. These are the edges. This is the theorem that only 2 cases are possible. And this is the topological sort. This graph is the way the people dress up, I think, right? You gotta put the tie before you put the jacket, and the belt before, the shirt before you put the belt, so on and so forth, right? So it's a DAG. Is this dressing up really a DAG? This is example here, but can it be that dressing up has cycles in it? What would that mean? If dressing up would have cycles, what would happen? You can't really dress up. Because to put an item, you have to have other items, and there's a cycle. You can't decide to put one of them. Everyone has prior dependencies, right? So very simple things like this can be represented like graphs. And here's the topological sort. According to the theorem, the one that you have to prove, there is a way to sort those things so that all the arrows goes to the right. So again, you have to get those discovery and finish times and figure out how you want to sort those. It's a simple thing to get the arrows go to the right. Now, for all DAGs, when somebody says DAG to you or the problem has a DAG, immediately use this. The reason for this is that every time you process a DAG, will be a lot easier if you have it sorted this way for all kinds of purposes. So in any interview or problem, when you know you have a DAG, immediately think of it as a linear sort of the vertices with all the edges coming this way. That's what we did for dynamic programming in effect, right? What we did, we have all these problems and subproblems. Sometimes the table was 2D, sometimes was 3D, 4D, whatever. Because it's a DAG, it can be arranged in an order, so all the arrows go from one into the other. Now, if this is my dynamic programming problem, it tells me how to start solving the subproblems, right? In dynamic programming, we put the arrows to the dependent problem. We say this problem is dependent to that problem. So if this would be my computation table DAG sorted, where would I start solving problems? These ones first, because this does not depend on anything. Okay? So what we really did, but we didn't call it topological sort. We took that computation table and we said, if there are no cycles, there is a sort. And we then figure out, okay, if you sort it this way, then you solve the problems. We didn't do this, we didn't call it topological sort. We tried to guess it, right? We look at that matrix chain multiplication and say, what order should I use solve these problems to avoid requirements that I haven't solved yet already? This, generally speaking, it's a case of topological sort because the computation problem, dynamic programming, is a DAG. So there is a way to sort it so that you can never have to go against an arrow. So the last piece that we need to do, and we won't finish it today, but it's something I think you've seen, but not the proofs of it. So the proofs we have to do. It's if I have a graph like this one, it's a directed graph. I can break it into strongly connected components. In undirected sense, connected and strongly connected means the same thing. It's an undirected sense. If I reach from U to V, I can reach back from V to U. But in a directed sense, this is not true. I can reach from V to U, but not from U to V. This is the case I had on the graph I showed you, the DFS graph. The reason I needed two DFS, because I pick a node A that didn't reach to some other node, C and H. But if I pick C, I could have reached the whole graph. So is that connected or not connected? That's my question. If we go back to this graph, this is the same graph I use for DFS. See, if you start in C, you reach everywhere. But if you start in A, you don't reach C. So is this connected or not? That's why we need the notion of strongly connected. We call this weakly connected, as in there is a way between C and H to reach from one to the other, but not backwards. In other words, there is no break, physical break between the graph. If I can draw some sort of, put my hand somewhere and there's no edge here, obviously those points are disconnected from the other points if there is a gap. In here, there's no gap. There are lines between the sides, but it's not strongly connected because from A, I cannot reach to C. So what is this doing here? It's saying, here are the strongly connected parts of this graph. A, B, and E are strongly connected because you can reach from anywhere to anywhere in there. Then, this is a strongly connected component, right? It can be reached from anywhere to anywhere, right, in it. But from this component, I can reach in here, but not backwards. From this, I cannot reach in there, right? And then what else? This is a strongly connected component. Actually, the whole thing is a strongly connected component, right? D, C, no. This is a connected component, and then this is its own node. Is that it? Yeah. So this is a connected component because I can reach from anywhere to anywhere. This piece is a connected component. this piece is a connected component, and this piece is by itself.
What does it mean by itself?
Like, it's not part of any other strongly connected component. If this would be the same with D or the same with C, there's no way from here to reach anywhere other than H. So the strongly component, what's the property between two component, strongly component, connected components? If I reach from one to the other, can I reach from this one back to that one?
Yes.
No. If that would be true, if I can reach from this component there and from this component here, this will be, in fact, one component, right? Because those are maximal. When we talk about strongly connected components, if I can reach from this component into here, which is true, see this arrow, I can reach, but if I could reach also backwards, the whole thing will be a component, right? So the strongly component graph, if I just look at this not as edges, but I look at the components this way, I group one component, ABE, that's reachable. I do CD, FG, those are the other two components, and this is by itself. It's not possible to reach from there to there and from there to there, because that will collapse the two into one. So the question is, how do we find these components? There is a highlights here that the projector does not display that shows the components. How can I find this is a connected component, this is a connected component, this is a connected component, and so on and so forth? This is not a small problem. I mean, it's easy to solve, but coming up with a solution is not that easy. And this, I'm sure, was not required for your undergraduate course, but it is required now. How do you find strongly connected components, and why does it work? The idea is to run DFS twice. Run it once, and run it the second time very specifically by the discovery and finishing time of the first run. So the second run has to be very carefully orchestrated to run exactly in a particular order. That's what we're going to do next time. Say the first DFS, it's easy. Run DFS whatever. Get the discovery and finishing time. So in here, the discovery time, the biggest finish time is this B, I think, for the first DFS. The second DFS has to start in B to work. So this concludes what you should know. I think you have seen strongly connected components before, what they are. It's very easy to understand what they are. In a component, I reach from anywhere to anywhere. And I could reach to another component with a condition that I can come back. So if I look at this is a DAG between those components, right? From this one, from AB, I can reach to CD, I can reach to FG, but not backwards. The red arrows have to do with how the second DFS works. Okay? So there will be a homework, in fact, many homeworks about graphs. One that I'm going to put up today, even though you still have, I think, until Monday to finish the hips. So we'll have 3 or 4, I think all the modules until the end, about 3-4 weeks at graphs.
Like if you have and you will get one here and one there and one there.